Okay, thank you very much for the kind introduction. I am, as she said, a doctoral student in the molecular plant breeding group, and I hope to walk you through some of the opportunities and limitations I found while developing a deep learning-based multi-environmental genomic prediction model. To give some context, even though I've seen it might not be needed, of course, multi-environment genomic prediction, I will shorten it as MAGP, aims at capturing these genomic per-environment interactions by using both genetic and environmental data. The increasing amount of complexity and data might be challenging in the future for statistical models, as we see. The amount, and also we've also seen that different streams can be integrated potentially, so this could pose a problem. And on the other hand, deep learning can efficiently address these challenges because of the nature of their algorithms. But currently, deep learning-based models do not usually outperform the statistical ones. In this context, one of the chapters of my thesis that I will be hopefully presenting soon aimed at establishing a pipeline to implement and optimize a custom DL-based multi-environment genomic prediction model in different data sets, and then compare it to some kernel-based approaches in real-life prediction scenarios from a machine learning point of view. But here, for time constraints, I will be focusing in one of the data sets, and it's the Maze Genomes to Fields data set, which I have browsed in some abstracts, and I believe some of you are familiar with it. But for the ones that are not, I will give just a quick overview. This was enabled by this initiative, and it's a multi-environmental data set spanning data from 2014 to 2022, and amounting to around a total of 255 environments, depending on the trait you're looking at. It has more than 4,000 hybrids, and it's genotyped with around 81K SNPs after quality control and filtering. Additionally, we retrieved the data using positional data for weather, the NASA-powered database, and for soil, we used the SoilDB package in R. A bit about the traits we included in the analysis. They are anthesis and silking, which are related to the male and female parts maturity in corn. Then we have this funny trait which combines these two, which is ASI, anthesis to silking interval, and it's just the subtraction of these two. And finally, yield, of course. A bit on how they look. Anthesis and silking are very similarly distributed. They are both measured in days, similar heritability, and a similar amount of records, genotypes, and environments. Then, when combining them both, of course, it's a unitless trait with lower heritability, lower number of records, and lower, around the same number of genotypes, but lower environment. And then yield, very nicely distributed trait with mean around 10 tons per hectare, moderate to high heritability, I would say, and the highest number of data records for the analysis. Then we have to approach how are we splitting this, why are we doing this? So we thought we will approach it from the machine learning side and split the data in train, validation, and test. And we want it to make sense, so we want to predict next year. So the easy way was to split the data in this way, where the trained set would be around 80% of the data. For those not familiar with deep learning, the training set is used to set the model weights, because the model adjusts its parameters by looking at this data and trying to mimic it as much as possible by minimizing the loss function. Then we have the validation set, which in this case it's around 10% of the data, and it's used to monitor the training dynamics, and we could do things like early stopping because we always know the metrics we're measuring or we're interested in through the training procedure. And finally, we have a test set, which serves as a final unbiased estimation of our model performance. Good strategy is to look that your unique environments and genotypes are well distributed in the validation and test set, which happened, of course, for the nature of the split to be the case for environments. But when we looked at genotypes, we found that there was a 0% overlap of unique genotypes in the validation set. Why is this? This is because of the way they have the data organized. Here it's a very simple representation. This does not depict the real data, but what we can see is that we have a problem, or at least I saw it as a problem, of a biannual turnover of genotypes. What this implies is that we will not have unique genotypes in the validation set. So what we did to solve this was to manually set around 10% of the training set into validation. And then in this way, we go back and we fixed this unique balance of genotypes and environments in our testing and validation set. Then for the pre-processing of the data, this is deep learning usually doesn't require as much as feature engineering or selection, but we still performed some in the SNP data because for the architecture we proposed, it was very difficult to fit computationally all the SNPs. So we performed feature selection by fitting extreme gradient boosting regressor with the blobs of the training set. We did this for 25 folds, and we recorded the feature importance for every fold, retrieving 250 SNPs per fold. This amounted in this reduced set of SNPs per trait, which are ideally correlated or have a high impact in that trait. Then the weather was just averaged, and the soil was left untouched. And then into the architecture of the model. The weather is a time series. I didn't do anything else than averaging per 5-day windows. So we directly fit this into LSTM layers, a couple of them. What are LSTM layers? They are long short-term memory. It's architecture that can process multidimensional data. It can store information on the series it sees and learns to recognize patterns by remembering or forgetting important bits of the sequence. Then the rest of the input was just passed through dense layers, which I call the shared layers. Then they were concatenated and allowed to also train a bit through a series of final layers. Here's the hyperparameter space that I will not go into detail, but what I would like to point out is that we did a two-step hyperparameter tuning. We first did a grid search with the extreme values and some in the middle. So we kind of saw some promising regions, and then we kind of subsetted this and performed more through hyperparameter tuning using Optuna, which is uses a kind of Bayesian optimization. And then the best set of hyperparameters was used to fit the models. How did we evaluate them? Or what did we benchmark it against? Well, we used the kernel-based method approach as a baseline adapted from Harkin 2014. And we calculated metrics in two ways, overall and per environment. Also, this tweak I did with the validation set allows us to compute this for the whole set, but also we can split it in three scenarios: unknown genotypes or known environments in combinations, which will be abbreviated like this for the following slides. Let me walk you through the results. This is not a correlogram, this is a heat map. And on the x-axis we can see the three splitting scenarios, and on the left we can see the traits. This is overall. So overall, deep learning performs better than the kernel-based method, but we have to note that in the second scenario, where the genotypes are known and the environments are known, it's pretty much the same, or kernel it's even better. The same doesn't happen for per environment, so here the performance is pretty much the same. I forgot to mention that the colors go from 1 to -1, blue to red. And then I will show the same slide, but for the root mean squared error. And here the story changes a bit, where deep learning consistently gets a better grasp on the root mean squared error in both cases, but the kernel-based approach still performs very well when the genotype is unknown, but the environment is known. Some of the traits are very off, and let me walk you through the 3 subsplits in a side-by-side scatter plot, where in the x-axis we have the true values, and in the y, the predicted values. And then this is the first scenario where the genotype is not known and the environment is known. Kind of similar. In this case, if this is your target prediction, I would go for the kernel-based approach. It's easier. You don't have to worry about any of that. Okay, thank you. Next scenario, where the genotype is known and the environment is known. Here we can see, I forgot to mention that every color is one of the environments, sorry. Here we can see where these high values for root mean squared error come from when you compute the overall metrics or in general. But if you're interested in per environment performance, then just go for the kernel, because if you're only interested also in the correlation, in this case the root mean squared error, it's also not that good. The same happens, of course, when both are known. Here are both not very good performers, but I guess this is the million-dollar question, and this is how they look when you combine all of them together. So, as a take-home message or conclusions of this modeling strategy, I believe that our proposed deep learning-based method is suitable for multi-environment genomic prediction in this case. And this method in this maze data set, although we've applied it to a couple more and it generalizes, it kind of accurately predicts in scenarios with novel environments, or maybe accurately was not the best word choice. It's better than kernel-based methods in general regarding when you compute an overall metric for the set, and it's comparable to kernel-based methods in terms of correlation regarding average metrics across environments. How I see this could be a promising approach to be prepared to breed for future scenarios where breeding for unknown environments is the question. And what I still need to get done before I finish writing the thesis, I thought on reducing the dataset recursively to explore the lower limits of this modeling strategy. Compute the test set, which I didn't want to do until I was sure that this is how I wanted the model to work, and apply the pipeline for our with dataset, which it's almost done, but I didn't show it. I want to thank my supervisors, Steven and Bruno. I also want to thank very much Daniel, who's in the crowd, and Michaela as well, because they made this possible. And you can see a cute picture of our group. And contact me if you have any questions.